Okay, good afternoon, everyone. Thank you for attending our first talk by our honor students. This will be the first presentation of Mr. Derick and then Mr. Heinrich Schultz. Well, first up is Mr. Derick. He'll be speaking to us on computing conjugacy classes of some finite groups of extension type, and he's being supervised by Dr. Prince and co-supervised by Mr. Zulvini. We will allow him to do his presentation, and after that, if you have questions, I will allow time for questions. Thank you. Over to you, Mr. Hill.
Thank you very much, Mr. Peterson. Good afternoon, everyone. I can't see everyone who's here, but I do thank you all for taking the time out of your day to watch my presentation. I am going to turn my camera on just for the first slide so I can say hello to everyone. I should be here. Hello, everyone. As you can see, I look a bit different than I did in this photo. I stole Dr. Vik's haircut. I thought I'd get some of his brains with it. So far, it's not working out too well, but we'll see. So we're going to start off with two basic definitions. Since I am computing conjugacy classes, it would only be right to start off with the definition of a conjugacy class. If we have a group G...
Mr. Hill, at the moment, your screen is not showing. Well, not by me. I just see a black screen. Are they? Okay.
All right. Do you see the next slide now?
Yes, I can see that slide.
Fantastic. Okay. So we have the definition of a conjugacy class. A conjugacy class is a conjugacy class of an element X is the set of all the elements conjugate to that element X. Conjugation is an equivalence relation, so we can partition a group into its conjugacy classes. And as an example here, we have S3, the symmetric group of three elements, or symmetries of three elements. And we can see that we have three conjugacy classes. Something interesting to note is all the different n cycles are in their own conjugacy class. So here we have the only one cycle, which is identity. We've got two cycles, all in the same class, and three cycles, all in the same class. Our next definition is that of a group extension. Since we are computing the conjugacy classes of groups of extension type, we should know what a group extension is. So if we have two groups, K and Q, an extension of K by Q is a group G such that K is normal in G, and the quotient group G mod K is isomorphic to Q. And then we just have a very simple example. Z4 is a group extension of Z2 by Z2, and this dot is how we denote a group extension. Right, so a bit of motivation behind why we want to compute conjugacy classes of these group extensions. I have a quote here from Professor Daniel Bump of Stanford University, and he says, "The most coveted piece of information about a group is its character table." Now, I think my next hairstyle is definitely going to be this guy's. What is a character table? So a character table is a tabulation of a group's irreducible characters. Now, this has a lot to do with representation theory and character theory, which we're not going to go too much into in this presentation, but it is just to show why we want these conjugacy classes. Character tables are used by physical scientists to do fancy things like classify molecular vibrations, predict whether a transition between two states is forbidden, and more. And I forbid you to ask me any questions on that afterwards, because that is definitely not my field of expertise. But character tables can also tell us as mathematicians a lot about the associated groups. Here is an example of a character table, and we have the character table of S3. Now, I want you to notice here the column headings over here. We have a 1 cycle, we have a 3 cycle, and we have a 2 cycle. This reminds us of the conjugacy classes of S3 that we just went over a minute ago. So there is a relation between conjugacy classes and character table, and the character table is a tabulation of irreducible characters. So we have this theorem over here, and the theorem says the number of irreducible characters of a group G equals the number of conjugacy classes of G. So there we have our motivation for finding the conjugacy classes of these group extensions. To find the character table, which as that Professor Bump said is the most coveted piece of information for a group, we need the conjugacy classes. So that's what we'll be doing today. We're going to go through a few more basic definitions. We have that of a group action. If we have a set X and a group G with identity E, the group action is a mapping G cross X to X, such that these two conditions hold. So we have that if we act GH on X, it's the same as acting H on X and then G on X. And then we have, if we act the identity on X, we need to get X again. Later on in this talk, we'll denote group actions not by this dot, but by exponentiation notation. So instead of saying G dot X, we'll say X exponent G. All right, but we'll see how that all works out later on. Next basic definition, we have that of an orbit. So if we have a group action and we act that group G.
I'm still looking at the slide on which you inked 1, 3, and 2 on the character table. So the slide hasn't progressed on my side.
Okay. Oh, I'm sorry about this.
Unless I've got a poor connection, so the other colleagues can just indicate if they are still looking at the character table also of CS3 or whether it's just me.
We have a problem, Quentin, because I see it nicely as you continue.
Okay, no, it's fine. Then you can go on. Don't worry with me.
Okay, I'm sorry. Sorry that you're having this issue, but
no, it's fine. I'll just leave and come back. It's fine.
Okay, all right. Where were we? We were at the orbit. Now, if we have a group acting on a set X, the orbit of an element X, is all the elements that G takes that element X to. All right. Next, we have a stabilizer, and the stabilizer is the all the elements of G. So when we act G on X, all the elements of G that take X right back to X, that make up our stabilizer. Next, this one we should all know is that of a centralizer. So the centralizer of X in G is all the elements X in G such that xg equals gx. Sorry, I think this should be G an element of G. So it's all the elements that commute with our element X. Now let's put all of these definitions into an example. Our first definition was that of a group action. So conjugation is an example of a group action where a group acts on itself. The orbit of the element X would then be its conjugacy class, and the stabilizer of X would also be its centralizer, since we can see that the stabilizer, which would then be Gx, G minus 1 equals X. If we take this G over to that side, we have Gx equals Xg, which is our centralizer of X in G. Now we can get on to the fun stuff. So we'll be using a method known as coset analysis to find the conjugacy classes of these groups of extension type. This method was developed by Professor Muri of Northwest University. And although it can be used to find conjugacy classes of group extensions in general, today we're just going to focus on finding the conjugacy classes of split extensions, which are equivalent to something known as a semi-direct product. So what is a semi-direct product? Let's say we have a group G, and it has subgroups K and Q. We denote it by this symbol over here. And it is a semi-direct product if K is normal in G, if KQ equals G, and if the intersection of K and Q is the identity element. All right. One more note on semi-direct products. Since K is normal, we can see K is normal in G. We have that QK has to equal K prime for some K prime in K and K in K and Q in Q. So if we have QK, Q minus 1, we can replace this QK with K prime Q, and then K prime, then Q minus 1 falls away as it's the identity, and we get K prime. Therefore, we can say Q acts on K by conjugation. However, in two different groups, this action could be different. So we need to add in a bit more information. We let theta, which is the mapping from Q, or is a homomorphism, actually, to be specific, from Q to the automorphism group of K, we let that be the conjugation action of Q on K. And we say that the semi-direct product of K and Q realizes theta. And we'll see how that works in a moment. We're briefly going to go through the theory behind coset analysis. I can prove all of this, but I have left out a large chunk of all the longer proofs just for time. So let's say we have a semi-direct product of K by Q. We say that is G, where K is abelian. Every element Y and G can be uniquely expressed in the form Y equals Kx, where K is in K and X is in, sorry, that should be Q. Furthermore, if we have an element in the intersection between two cosets, such cosets Kx and Ky, where X is not equal to Y, then the intersection of those cosets is the empty set. There's no elements in common. Therefore, we only need to consider one coset, Kx, for each conjugacy class of Q with representative X. For a element X in Q, we define this Cx as the centralizer of Kx in our big group G. Cx is a subgroup of G because any subset of G, the centralizer of that in G is going to be a subgroup of G. Since this is a subgroup of G, we can act this on our Kx by the action of conjugation. Now we can show that this Cx is itself a semi-direct product of K by the centralizer or the stabilizer of X in Q, since all three of those conditions hold. So as mentioned before, we have that Cx acts on this coset Kx by conjugation. Since it is a semi-direct product, the Cx, we can write Cx as K-CQX. So if we act Cx on an element Kx in the coset Kx, that's the same as acting this K-CQX. And since the group action, this is the same as first acting K on Kx and then acting CQX on that acted on Kx. Therefore, we can consider the actions of K and CQX on Kx separately. So since we first act K on our coset Kx, we're going to look at that action first. But before we do that, we need to look at this great theorem over here. This is the orbit stabilizer theorem, which tells us that if we have a group G that acts on a set X, then the orbit of X, the order of the orbit of X, is equal to the order of G divided by the order of the stabilizer of X. This is going to come very much in handy in the next few slides. So as I said, we first look at the action of K on Kx. If we let CKX equal, so this would be the stabilizer of X in K, we can actually do some maths here and we can change this. So since we have conjugation as our action, this is the same as saying kx k minus 1 equals x. And then if we change that up a bit, we can get that that is the same as k element of k, where kx equals k. So this is the same as the stabilizer of what is that, k in q, or what are we? Basically, we acting this x now on the k, whereas here we acted the k on the x. This equivalence is going to come in handy when we actually do the work. Now we can show that the ckx equals ckz for any z in kx, and now we say that the action of k on z produces the set where z is in kx, is the acted on elements of k, and we get that of kx, and when we act k on these elements of kx, we get an orbit which we are going to call qz. So when we act k on kx, it splits into these orbits. We say that the order of ckx is equal to I, and so we have that the size of all these orbits by the orbit stabilizer theorem is the order of k over the order of ckx, which we call I. So in summary, the action of k on kx, kx splits into I orbits, and we have this equation here, which we will use soon again. Next, we consider the action of cqx on kx. So we are going to act cqx on these orbits. So this is the stabilizer of x in q, which is the centralizer of the conjugacy class of x. So under this action, we suppose that f of the orbits, q1, q2, etc., form an orbit delta f. So f of them fuse together and form this delta f. Then from the previous slide, we can get this equation. And now we let y be an element of this orbit that we end up with. The size of the conjugacy class with representative y from that delta f is equal to the size of delta f times the size of the conjugacy class of x and q, since the cosets are disjoint. By the orbit stabilizer theorem, we can replace that size of the conjugate class of y and g with this size of g over the centralizer of g and y, y and g. We replace this size of delta f with the previous equation, which gives us that size. And by the orbit stabilizer theorem again, we can get this q over cqx, the orders of those two. And then we get a k times q over here, which is our group G. And after doing a bit of simple algebra, we can get a formula for the centralizer of y in G, which is the centralizer of the conjugacy class of G. And we see that all we need to work out then are these i's and these f's, considering we already will have this cqx. So in summary, the theory of it, if we have the conjugacy classes of Q, we choose a representative x, and now we're going to represent that kx, that coset, by this pact of chewing gum. We act k on it, and we get a bunch of orbits. We get I orbits, to be specific. Then we act cqx on it, and some of them may fuse, and we get these deltas. And from there, we can work out the centralizer of y in G. Now let's quickly do a real-life example. We're given the problem that we want to find the conjugacy classes of the group with structure 2,4, to split extension S5. So that colon means a split extension, which I already said is the same as a semi-direct product. We are given that S5 has a representation, a 4x4 matrix representation, generated by these two matrices, and 2 power 4, or not exactly a power, but this is the elementary abelian 2 group, consisting of elements 1, E1, E2, E3, E4, E1, E2, all the way up to E1, E2, E3, E4, where the order of all the elements except for the identity is 2. Using some MATLAB code over here, I could compute the size of the conjugacy classes. I could separate them into conjugacy classes, and I could find the order of the centralizers of those conjugacy classes, which we will need just now. Here's the MATLAB code. I'm very thankful that none of my computer science lecturers are here, because I think they would fail me for that. It's not exactly optimized. But finally, one more note. I mentioned that we need a specific action to kind of use in place of what we know as conjugation. So since this 2,4 is isomorphic to the vector space of dimension 4 over the field of 2 elements, we can write any element of this 2,4 as a vector. So let's say E1 we can write as the vector 1, 0, 0, 0. Let's say 2, E4 can be written as 0, 1, 0, 1. And what this allows us to do is use the natural action of a matrix on a vector by multiplying a matrix with this 4x4, one of these 4x4 matrices, by this vector, and we get another vector out. So that is going to be our that natural action is basically the theta that our semi-direct product realizes, or is realized by. So let's start. So our the first thing we have to do is choose a representative from each conjugacy class. So the first conjugacy class we're looking at is the one, the identity. So we don't have any choices to make here. We just choose X to be the identity. So if we act X on each element of K, we obviously have that it fixes each element. So our CKX is K, and thus the size of that, which is our I, is 16. So the centralizer of X and Q is also Q, and the size of that is 120. It's the whole group. So we simply plug in those values that we have, and we get that the centralizer of Y and G is equal to 16 times 120 over F. So now we need that F. Since K splits Kx into 16 orbits, each element of Kx gets to be in its own orbit. Now we first consider the action of, so we've considered the action of K on Kx. Now we consider the action of CQX on each of those orbits. So we first act CQX onto the first orbit, and we get that we just get that orbit back. So our first delta is going to be equal to Q1. So we get the size of that delta, and we can get that value of F, and thus we have our first class, which has a centralizer of order 1920, which is our entire G. Next, we do that same process, and we find that when we act CQX on Q2, we get this orbit with 5 elements, and we plug in the values again. We get our second class, and we get the size of its centralizer. Then we do it again, and we get our delta 3. We plug in all those values again, and we get the order of the centralizer. Here's a bit of a more interesting example. Instead of x fixing all of these elements, we have that x takes the elements to a certain other element. So, for instance, here it takes E1 to E4, it fixes E2, and so on and so on. So we can represent our action of x on our group K by the cycle structure. And if we look at all the elements that are fixed, we can easily see it now, and thus we can find our I value. So our I is equal to the number of elements that are fixed. Now we consider the action of K on Kx. So since I is equal to 8 in this case, we have 8 orbits, and they each contain 16 over 8. So that's the size of K divided by I, 2 elements. So we take our first element x of our Kx. We act E1 on it. We do this clever mathematics here, and we get the value E1, E4. Then we act E2 on x, and we get the value x. Now we have 2 elements, and we know that this is going to be our first orbit. We keep doing that until we only have 2 elements left, and then we know that those 2 elements are going to be in our last orbit. Using MATLAB, I got the centralizer of x and q. We get the size of that centralizer, we plug in the values, and we get all our different classes. Now, I'm not going to go through, in the interest of time, I'm not going to go through every one, but as you can see, it repeats for every class. Here's our next class, our conjugacy class of Q. Next one again, and next one again, next one again, next one again, and what we left with is this wonderful table here, which shows that how each conjugacy class of Q basically splits into these conjugacy classes of our entire group G, and we have the orders of the centralizers. Thank you very much for listening. It's really been a pleasure presenting this, and I guess now I can be open to questions.
Thank you, Mr. Hill. You can hear the excitement in your speaking. Colleagues, students, if you have any questions, Mr. Hill is ready for you. Just remember to unmute if you're going to ask a question.
Just a question which I have about the orbit stabilizer. How does the orbit stabilizer theorem quantify the relationship between the size of the orbit and the size of the stabilizer subgroup?
All right, let me just get back to that slide. All right, so the orbit stabilizer theorem tells us that if we have any group action that acts on a set X, the size of that orbit is the index of the stabilizer in G. So that's and that is equal to the size of G over the size of the stabilizer of X.
Okay, thank you.
No problem. Thank you for the question.
Any other questions or comments? Mr. Hill, thank you very much for your talk. You can close your presentation, and Mr. Schultz, you can open your presentation.
All right. Thank you very much, everyone.
Thank you. Thank you very much. We can see your slides.
Okay, can
You might
everybody
want to
see?
go- Yes, we can. Well, I can. You might want to go full screen on your slides.
Is it
That's
full?
up to
Is
you.
it working?
I can see your slides on the left-hand side of your PowerPoint, so I don't know if you want that. If you want that, that's fine also. Or do you want to do a slideshow? But anyway, it's up to you how you want to do it. For me, that's clear. I can see everything. Colleagues, our second speaker is Mr. Heinrich Schultz. He'll be speaking to us on the Brouwer and Schauder fixed point theorems with applications. Mr. Schultz, who's your project supervisor?
My project supervisor is Dr. Weicht.
Hi, under Dr. Weich's supervision. Again, while the speaker is speaking, I will keep quiet. Even if I can't see what's happening, I will just ask in the chat so as to not interrupt you like I did with Mr. Hill. So we will leave questions and such until the end of the presentation, and then we can ask the questions we want to ask. So Mr. Schultz, if you're ready, you can take over.
Thank you very much. Good afternoon, everyone. My name is Heinrich, and I'll be doing my presentation on the Brouwer and Schauder fixed point theorems with applications. So the Brouwer theorem states that any continuous self-map of a closed unit ball of a finite dimensional space possesses a fixed point. This theorem, known as the Brouwer fixed point theorem, is one of the most renowned and significant principles of existence in mathematics, and was discovered by Lutz and Gqeberha Jan Brouwer between 1909 and 1913, and it has played a transformative role in the field of topology. Brouwer, a Dutch mathematician, is credited for establishing mathematical intuitionism and effecting a complete renovation of topology. The Schauder theorem states that any compact continuous self-map of a closed unit ball of a Banach space possesses a fixed point. Now, Julius Schauder, or Juliek Schauder, is a Polish mathematician renowned for his contributions to functional analysis, partial differential equations, and mathematical physics, and introduced this fixed point theorem for infinite dimensional spaces, or Banach spaces, in 1930. In his proof, Schauder utilized compactness arguments to demonstrate the existence of fixed points. And sorry, there are two versions regarding his death, though. So in the first version, he was betrayed by the Gestapo, leading to his arrest, and like many other Jews, he vanished without a trace. The second version suggests that he was shot by the Gestapo during one of their routine searches for the Jews in September 1943. So for the rest of this presentation, we will investigate, discuss, and prove the Brouwer and Schauder fixed point theorems using three different methods. The chapter that follows, chapter 2, which reviews definitions and theorems needed to understand the main body of work. And then in chapter 3, the main results, we will introduce specific notation and define mathematical structures and tools needed for the rest of the chapter. What is useful in proving the Brouwer and Schauder fixed point theorems in chapter 3 are the following results. The Gell-Mann theorem, which states that if we let V be a Banach space and K mapping S tilde to V an odd continuous compact map, then there exists a point in S tilde such that K of X star T star is equal to X star, i.e. the set of fixed points of K is non-empty. The second result that is important is the Borshak-Ulam theorem, which states that if we assume that V is a finite dimensional is finite dimensional and G maps S tilde to V is a continuous map, then the set of antipodes AG is non-empty.
Sorry, Mr. Schultz, I have to interrupt you. For me, I see your slides are not progressing, and Dr. White says he also has the same problem.
Yes, that is not a problem. We are still on the first slide. Sorry.
Okay, I'm still looking at the introduction.
Yeah, no, that is
Okay.
where we're supposed to be.
Okay, no, that's fine then. Sorry, that's fine.
Sure. So after the Borsak-Ulam theorem, we will then proceed by showing how the Kalman theorem and the Borsak-Ulam theorem leads to proofs of the Brouwer and Schauder fixed point theorems. And then after that, we will introduce two alternatives to proposition 1, which we will see a little bit later. And then lastly, in chapter 4, we will show a surprising application of the Brouwer's fixed point theorem, namely the proof of the fundamental theorem of algebra, which was first proved by Carl Friedrich Gauss in 1799. So Gauss's proof of the fundamental theorem of algebra used algebraic and geometric reasoning, linking the behavior of the polynomials, real and imaginary parts, in the complex plane to prove the existence of complex roots. But the proofs that followed Gauss's proof using analysis turned out to be much more elegant. So now the preliminaries. So we have a metric space. A metric space is a pair XD, where X is a set and D is a metric on X, or a distance function on X. That is a function defined on X cross X, such that for all X, Y, Z in X, we have that D is real valued, finite, and non-negative. D of X, Y is equal to 0 if and only if X is equal to Y. D of xy is equal to d of yx, and d of xy is less than or equal to d of xz plus d of zy. Then we have the norm. The norm is a real or a norm on a real or complex vector space. X is a real valued function on X, whose value at an element X in X is denoted by the norm of X, and it has the following properties. The norm of X is non-negative. It is equal to 0 if and only if X is equal to 0. The norm of alpha X is equal to the absolute value of alpha multiplied by the norm of X. And then we have the triangle inequality over here, which is the norm of X plus Y is less than or equal to the norm of X plus the norm of Y. And so alpha is any scalar and X and Y are arbitrary vectors in X. So then a normed space, X is a vector space with a norm defined on it. And then a Banach space is a complete normed space, i.e. it is complete in the metric dxy, which is equal to the norm of X minus Y, and defined by the norm. And then a compact set. So metric space X is said to be compact if every sequence in X has a convergent subsequence. And a subset M of X is said to be compact if M is compact, considered as a subspace of X. And then the last couple preliminaries are a compact function between two norms. So if we let X and Y be normed spaces, then T mapping X to Y is called a compact mapping if the closure of TB is compact, where B is the closed unit ball of X. Then 2 points are antipodal, i.e. each is the antipode of the other, if they are diametrically opposite to one another. And then finally, we have a continuous mapping theorem, which states that if we have X and Y that are metric spaces and T mapping X to Y as a continuous mapping, then the image of a compact subset M of X under T is compact. Now we will move on to the main results. So we'll start off with some notation, mathematical structures and tools as required. So we let V be a normed vector space that is n-dimensional, and it is also a Banach space. B and S are the closed unit ball and sphere of V. F is a self map of B, and fix F is the set of fixed points of F. And then S tilde is this lovely space over here. And then G maps S tilde to V, and AG is the set of antipodes on S tilde. And then V tilde is the cross product of V and R, and it's equipped with the norm, which is equal to the maximum of the norm of X and the absolute value of T. V tilde is also a Banach space because V is also a Banach space. And then finally, we have our set NK, which is the set of fixed points of K. So now the following items on this slide are required to prove the Brouwer and Schauder fixed point theorems. So we have the Gell-Mann theorem, which states that if we have a Banach space V and K mapping S tilde to V, an odd continuous compact map, then there exists a point X star T star in S tilde such that K of X star T star is equal to X star. And then the Borchak-Ulam theorem, which states that if we assume that V is finite dimensional, and G maps S tilde to V, is a continuous map, then the set of antipodes AG is non-empty. Then the crucial proposition, proposition 1, is if we let V be a Banach space and F a continuous compact self map, and then we let G map B tilde, which is the cross product of B and this closed set, to V, and we define it by this function G of xt. And then we also let K map B tilde to V be a map defined by this function K of xt. Then with all of these conditions in place, we can say that the set of antipodes AG across S tilde is equal to the set NK across S tilde, the set of fixed points of K. Now, then we have proposition 2, which states that if we assume that there exists a point X star T star in S tilde, such that G of X star T star is equal to G of negative X star negative T star, i.e. we have this equation over here that is satisfied, then either X star or negative X star is a fixed point of F. So now with these theorems and propositions, we can prove the Brouwer theorem. So the Brouwer theorem, as previously stated, says that any continuous self-map of a closed unit ball of a finite dimensional space possesses a fixed point. So the proof is as follows. So we use the Borchak-Ulam theorem, and we arrive at this, which basically states that the set of antipodes is non-empty. And now, because the set of antipodes is non-empty, we have that there must exist 2 points, X star T star and negative X star negative T star, that exist in the set AG. And so therefore, by proposition 2, since we have such a point in S tilde, because remember, if X star T star is in AG, then it has to be obviously in S tilde as well. So since we have such a point like that, that satisfies this condition of here, because it's also in the set AG, either X star or negative X star is a fixed point of F. So, and this gives us Brouwer's theorem. So then we can move on to the Schauder theorem, which states that any compact continuous self-map of a closed unit ball of a Banach space possesses a fixed point. And the proof here starts off with the Gell-Mann theorem. And so the Gell-Mann theorem allows us to have a point x star t star in S tilde such that k of x star t star is equal to x star, which means that we have that the set of fixed points of k, nk, is non-empty. Now, since nk is non-empty, we can deduce that the set AG across S tilde is non-empty, since we've already established by proposition 1 that the set nk is equal to the set AG. Now, because of that, we have that since AG across S tilde is non-empty, we know that there exists a point x star t star in S tilde such that g of xt is equal to g of negative x negative t. And so therefore either x star or negative x star is a fixed point of f by proposition 2. Now, f is a compact continuous self-map of a closed unit ball B of a Banach space V. And so therefore we have the Schauder theorem. Let me just go back. I forgot to mention. So with the Brouwer theorem, it relies heavily on the fact that the space has to be finite dimensional, and so therefore we can't use the Gell-Mann theorem for this proof. Okay, so before we move on to the exciting part, which is the application of fixed point theorems, I'll quickly show two alternatives. So alternative 1 is to use an admissible function. So we define R to map the closed set -1, 1 to R, and that's a function. And so R is admissible if it satisfies the following conditions. R is continuous, R is equal to 1 when t is equal to 1. The absolute value of R of t is less than or equal to 1 when t is between -1 and 1. And then for any t within the open set -1 to 1, at least one of these two, the absolute value of rt or the absolute value of r negative t, is strictly less than 1. So then with this admissible function, we can now define these functions gr and kr, which both map S tilde to V, with these two functions over here. So now the goal here is to be able to show that gr of x star t star is equal to gr of negative x star negative t star. And so using this admissible function, we are able to do so. So then Sue has another alternative to proposition 1, where he uses these two functions g and k, which are kind of similar, but they have their own unique twists. But what makes his alternative interesting is that he uses a function h, which also maps S tilde to V, but he defines it like this. So he has h of xt, which is equal to a half multiplied by g of negative x negative t minus g of xt. And so using this function h, he can show that g of negative x negative t is equal to g of xt. And so from there, you can swap out proposition 1 in your proof for this alternative. So the surprising application of the fixed point theorem. So we can prove the fundamental theorem of algebra using the Brouwer theorem. But before we do that, let's just state the fundamental theorem of algebra. So it says that if P is a polynomial with complex coefficients of degree n greater than 0, then there exists an element z in the complex numbers such that P of z is equal to 0. So I'll only be giving a little bit of a proof outline. So we start off by assuming that z to the power of n in the polynomial P of z is equal to 1/2. And then we also assume that P of z is non-zero for all z in the complex numbers. So after some calculations, we are able to define a new function, g of z, which is equal to z minus f of z, for z in D. And D is an open ball centered around 0 with radius big R, and f is the nth root of P. So then we can show using Brouwer's theorem that we can find a fixed point z0 such that g of z0 is equal to z0. And so therefore f of z0 is equal to 0. And from that, we have that P of z0 is equal to 0, and this is a contradiction. So it contradicts our initial assumption, and therefore there must exist an element, a complex element, such that P of z is equal to 0. Thank you for listening. And it was probably quite short and sweet, but I hope you enjoyed. If there are any questions, please just raise your hand so I can see you.
Thank you, Mr. Schultz. Thank you for your presentation. Very concise, very tight, very neat. Colleagues, students, if you have any questions for Mr. Schultz.
I see Derick has a question.
Yeah, go ahead, Mr. Neil.
Nice talk, thank you. You mentioned that Brouwer is the father of mathematical intuitionism. Now, after studying his work, would you consider yourself a mathematical intuitionist?
I agree with what he started with mathematical intuitionism, but I think, yeah, I think I do consider myself a mathematical intuitionist.
All right, thank you.
Any other questions or comments? Okay, it looks like we do not have any further questions from the group. Thank you for your presentation, students. You kept it tight, you kept it close. Thank you to the supervisors and co-supervisors. I'm sure you had some input in their presentations as well. I will stop the recording. And I will split it up into 2 separate videos for the 2 talks.